In this video, we're solving a kinetic friction problem where we have an applied force pointing down at an angle on a block. And because that has a vertical component, it's going to mess with the normal force in this problem, so we have to keep that in mind. And the problem is broken into parts. We're asked to make a complete force diagram at the beginning of the problem, which you should do anyway. And then in part B, we want to compute the normal force. Part C, get the kinetic friction force, and finally put it all together in part D and find the acceleration of this block. So we'll start building the force diagram, and the first thing I'm going to do is break this applied force of 30 newtons into its components. So our horizontal component is going to be given by 30 newtons times the cosine of 25 degrees. That's the adjacent side here. And when we run the numbers on this, we get about 27.2 newtons. Our vertical component points downward, but we're going to write the magnitude of it here. That's 30 sine of 25 degrees. And when we run the numbers on this one, we get about 12.7 newtons. Now it's probably nicest to view these force components attached to the block itself. So that's taken care of, and we have this downward 12.7 newtons and a rightward pointing 27.2 newtons. Next we can put in the force of gravity, and that's given by mg. And when we plug in the mass of this thing, 5 kilograms, and then g, 9.8 meters per second squared, we arrive at a weight, or a force of gravity, of 49 newtons. So now the normal force has to balance both of these downward vectors. That's why an applied force with a downward component changes the normal force. So that additional downward 12.7 newtons, the normal force has to take care of that to balance it. So there's our normal force, and we'll just leave that as an n for now, because in part B, that's where we're asked to actually compute this thing. The final force we need to get into this diagram is the friction force. So this applied force is going to cause the block to begin sliding to the right, which means a friction force arises pointing to the left, resisting the direction of the slipping. And for now, we'll just call that friction force little fk for the kinetic friction. So there's a complete force diagram, and now we can get into the rest of the problem. We're asked to compute the normal force on the block. And again, the normal force is going to do whatever it has to balance all the forces in the perpendicular direction to this surface. That means the normal force must be equal to 12.7 newtons plus the additional 49 newtons for the weight, and that's going to balance all of our perpendicular forces. This gives us a normal force of 61.7 newtons. Next, we compute the kinetic friction force, which is of course related to the normal force. That's given by the kinetic friction coefficient, mu k, multiplied by the normal force. So just as a reminder of what's going on here, because that applied force had a downward component, that caused the normal force to become more intense, which in turn causes the friction force to be more than it would be otherwise. So we plug in our kinetic friction coefficient that was given to us as 0.19 and our normal force, 61.7 newtons. And this gives us a kinetic friction force of 11.7 newtons. Finally, we can get the acceleration of the block. So what we're doing here is applying Newton's second law. So that's F net equals ma, and what we're talking about is the horizontal analysis of this, so the x direction analysis. And we have two forces acting in the x direction. There's our 27.2 newtons pointing to the right. That's the one that wins. And then our friction force, this 11.7 newtons pointing to the left, and that gives us our net force on the block horizontally. This is going to be equal to the mass of the block, that's 5 kilograms, times what we're looking for here, the x acceleration. So we smash the numbers into a calculator, we do the subtraction on the left and then divide by 5. And when we do this, we find an acceleration, just keeping our usual 3 significant digits here, of 3.10 meters per second squared. And that's it. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.